all. So today I will present my work, and thanks to Atomic Molecular and Optical Physics divisions of DRL to giving me opportunity to present my work. So what is astrochemistry? Astrochemistry is the study of the abundance and reactions of chemical elements and molecules in the universe and their interactions with radiation and their feedback on physics of the environment. So what is the role of interstellar molecules in the evolution of the universe? Various chemical species are often used as chemical pressure of different astrophysical conditions. So astrochemistry, often called as molecular astrophysics, and since it is an interdisciplinary field uh, containing astronomy, physics, chemistry, and biology. So in the recent state of art, astrochemistry includes observation, models, laboratory experiment, and computations. Today, in my presentation, I will mainly highlight the modeling part and computation parts supported with some experiment. So this is the list of known interstellar and circumstellar molecules. Almost 250 molecules have been discovered in ISM and CSM. The list is available in the CDMS website, and the list includes from diatomic molecules to up to 70 atoms molecules. And if you see this plot, you can see that cumulative number of detected molecules year-wise, and the first detected molecules from 1937 to 1940 to recent 2020, almost 250 molecules have been detected. It is more than 245, and if you see the last 15 years, that is since 2005, the rate of detections is 5.9 per year. So this is the periodic table containing known 118 elements. Out of them, only a 17, these are highlighted, only 17 constructed these interstellar species. Complex organic molecules. Unlike chemistry, core chemistry, in astrochemistry, astrobiology, we called complex organic molecules of them, for which carbon-bearing molecules containing 6 or more atoms. So they are mainly these types of key categories like alcohol, aldehyde, ketone, acid, ester, amide, sugar-related species like glycoldehyde, and other species like chiral molecule propylene oxide. All these molecules, and there are more, some not in the list, already observed in the interstellar medium and circumstellar envelope. So life cycle of the cloud. We know interstellar medium is highly heterogeneous medium compared to our Earth atmosphere, where temperature is roughly 300 Kelvin and density almost 19 molecules per cubic centimeter. And interstellar medium consists of several types of cloud, from diffuse cloud to dense cloud. There are protoplanetary disk, and then mass loss, and then again form diffuse cloud. So this is a cyclic process. Here in this picture, I show the low mass star formation step wise, like our sun, where prestellar phase exists, where formation of some simple molecules occurring, and then gradually planetesimal and planet forms, and complex organic molecules evolve in this whole time, and finally some biomolecules like glycine or amino acid, they uh, comet or asteroid, through comet or asteroid, they bombarded on early Earth condition. So in this presentation, I will mainly highlight this diffuse cloud region, dense cloud region, and highly radiated mass loss region or supernova remnant like things. So chemical evolution at interstellar dust. ISM consists 99% gas and 1% dust by mass. These dust perform an catalyst, not active or passive way, or direct or indirectly way. And if you see this example where carbon and hydrogen in the gas phase, they adsorb on the interstellar ice containing dust grain core of carbonaceous or silicate, and on that ice mantle layer exists, and this gas phase species accrete on the ice mantle and then react to form like CH4 by hydrogenation reaction, and then dissolve again in the gas phase when they find temperature greater than their binding energy. And this desorption occurs by various mechanical processes like thermal desorption, non-thermal desorption, chemical or reactive desorption. So my presentation mainly divided into two parts: radiation dominated region where some exotic molecules exist, and radiation shielded region where complex organic molecules form. So part one is the radiation dominated region, where I highlight diffuse clouds, supernova remnant, and photon dominated region. So discovery of first molecular ion in the universe, which is known as HeH+. Recently, it is detected by Houston and others in 2019 towards planetary nebula NGC 7027 by SOFIA space-based observation. And they detected the ground state rotational transition J equal to 10 towards this source in the range 149 micrometer. And it is important because HeH plus is known that first molecule formed in the universe after Big Bang when temperature falls below 4000 Kelvin due to high ionization potential than hydrogen atom. It neutralizes fast by recombines with available electron, and then neutral helium react with a proton to form HeH plus by radiative association reactions. So first H2 are formed via ion molecule reactions with HeH plus, and then after forming H2, several complex organic molecules or second order species formed. So first observed interstellar noble gas molecule is ARH plus 36 ARH plus, observed by Barlow and others in 2013 towards Crab Nebula via Herschel Spire instrument in the rotational transitions J21 and J10 with a prominent transitions of OH plus. And after that, Schilke and others in 2014, they observed the rotational ground state J equal to 10 of ARH plus, 36 ARH plus, towards several continuum sources like Sagittarius B2, W51, W31, W49, etc. And after that, in the same time, Richardson et al. 2013, they modeled several H2 emitting knots in the Crab region. Generally, in the interstellar medium, H2 formed by grain catalysis process. But in this environment, due to high radiation and high temperature, H2 form some other process. These are the mechanism they suggested, that is available electron react with hydrogen atom, ubiquitous hydrogen atom, to form H anion, and then H anion again reacts with H atom to form H2 molecule by associative detachment reaction. So these pathways is dominating to form H2 molecules in this environment. And there are papers by Low 2012. They observed some H2 emitting knots towards several H2 emitting knots towards several Crab nebula filamentary region. And motivated by these two work or these two observation, that is ARH plus observation and recently HEH plus observation, and we aim to study the formation of three hydronium ions, that is ARH plus, NEH plus, and HEH plus, as well as three hydroxyl ions, AROH plus, NEOH plus, HEOH plus, towards the Crab environment region. Why we choose HeOH plus or hydroxyl ions? Because OH plus also detected in this environment by Barlow and others. So for this, we prepared a realistic model for the diffuse ISM, and these are the input physical parameters considered in our model, and these are the input initial elemental abundances considered. For the modeling purpose, we used spectral synthesis code Cloudy, and this is the spectral energy distribution included in our modeling purpose. And there are also network of argon, neon, and helium chemistry, the huge network included in our modeling. And from the modeling result of diffuse ISM, you can see y-axis is the abundance of species in both window, and x-axis is the visual extension. So with increasing visual extension, you can see that H2 abundance is increasing. That is, from diffuse to dense region is going the cloud, and H is almost in atomic form, that is the cloud is till diffuse form, and temperature, you can see the red line curve, that is temperature varies from 25 to 50 Kelvin. And also you can see the C transform to C plus, sorry, C plus transform to C when we go into the depth of the cloud. And if you see the right hand side picture, here we can uh, we can plot some argonium, we can plot some noble gas hydride and hydroxyl cations, and check the fate of there, and see that ARH plus, that is dashed dotted line, is of the order of 10 to the power minus 9 abundance, and it is decreasing with increase the depth. That is ARH plus is forming in the diffuse environment, and it is a good tracer of diffuse cloud region where H2 density is very low. And then we prepared a realistic model for the crab. And for the crab modeling, we used same chemical network, only the parameter, physical parameters changed as an input parameter of cloud spectral synthesis code, and these are initial elemental abundances. And using our crab nebula modeling, we calculate surface brightness. That is, these are the intensity, specifically intensity of these transitions, ARH plus 1021, OH plus 971 gigahertz, and H to 2.12 micrometer. And highlighted value is the value of surface brightness in units of arc per centimeter square per second inverse per steradian inverse, observed value. And in the parameter space, we vary density along x-axis, and along y-axis we vary cosmic ray ionization rate. And we found that, and the contour here denoted the observed surface brightness value in every window. And we found that a high value of the cosmic ionization rate, about factor 10 to the power 6 to 10 to the power 7 than the average cosmic ray rate of the order of 1.7, 1.3 10 to the power minus 17. And this is roughly of the order of 10 to the power 6 times higher, with a total hydrogen density a few times 10 to the power 4 to 6 can successfully reproduce the observed absolute surface brightness. So in the crab environment, where we can observe these transitions, from our modeling results suggest that the density is 10 to the power 4 to 6, and cosmic ray ionization rate roughly of the order of 10 to the power 6 to 7 times higher. And then from the value of surface brightness, we check the detectability of these transitions. And for this, we selected 3 criteria. That is, number 1 is the optical depth value, and number 2 is the atmospheric transmission, calculated using online program ATRAN, and number 3 is the surface brightness value. Y-axis denote the surface brightness value, and compare if it is comparable to observed surface brightness values of OH plus in the crab region, also greater than OH plus. So these 2 lines denotes it is already observed transitions of ARH plus, and the other transitions could be observed, since these transitions 485 micrometer to 42 micrometer, they are successfully fulfill these 3 criteria, and we can identify these transitions with a space-based observation. So now I move to the next topic of interstellar phosphorus. Phosphorus is the 5th most important by mass after carbon, nitrogen, oxygen, hydrogen. It is biogenic element. It stores, transmits the genetic information in nucleic acid. It serves as precursors in the synthesis of RNA and DNA. It's also essential components of phospholipids. So phosphorus is an important biomolecule. It is important for astrobiology purpose. So recent detections of phosphines in the cloud decks of Venus, since then it is a hot topic to model phosphorus chemistry, and observed mainly in circumstellar envelope phosphorus bearing molecules is PN, PO, AHCP, CP, CCP, PH3, and only PN and PO is observed in the star forming region. So for this purpose, we modeled phosphorus chemistry in diffuse interstellar medium, motivated by work by Chantos et al. 2020, they attempted to observe these transitions, phosphorus-bearing molecules transitions towards extragalactic quasar source, this, and they could not observe these molecules, but they set an 3 sigma upper level of their detection. And following their modeling results, we also model in the diffuse ISM region, where cosmic ray ionization rate considered of the order of 10 to the power minus 16 and density 300 per cubic centimeter. And we model the diffuse cloud region, and from our modeling result, we check the fate of phosphorus bearing molecules in this similar environment, and uh, where they propose to observe, that is towards greater than AV, that is visual extension greater than 2 to 3, we check that PN and PO abundance, and we see that PO by PN ratio here less than 1, that is PO is lower than PN in this region. And then we check the fate of this species in the PDR region. And for PDR modeling, we again use spectral synthesis code cloudy, and we use the Rolik 2007 paper F4 PDR benchmark model, where gas temperature 50K, dust temperature 20K, density 10 to the power 5.5 per cubic centimeter, and interstellar radiation field in 10 to the power 5 drain unit, and cosmic ionization rate 5 into 10 to the power minus 17 per second. And considering these input physical parameters, we modeled PDR region, and check the fate of these species, and see that again PN is forming very high than PO. The reason behind that would be this reaction PO plus N forming PN plus O, that is high abundance of PO, and N, if you see in this window, the N abundance black curve is roughly of the order of 10 to the power minus 5 to 4. So high abundance of N converting PO to PN. So we get PN is very much higher than PO. So here in PDR region, PO by PN very less than 1. And now we move to our next part, which is dense cloud region, or radiation shielded region mainly. And here, since in the previous part, in the previous part, PH3 cannot be formed in this diffuse cloud environment or PDR region environment. It is very low abundance. So to check the abundance of PH3 or phosphine, we model hot core chemistry, hot core region. And for this modeling purpose, we used our gas grain chemical code, considering isothermal phase, isothermal collapsing phase, warm-up phase, and post-warm-up phase, and check that phosphine is forming very high abundance, roughly of the order of 10 to the power minus 10. And if we consider their destruction pathways using H and OH, which are not considered previous study, and we see that realistic estimation of their abundance roughly of the order of 10 to the power minus 12 to 13. This dotted dashed curve, this is a brown dashed curve. And if you see in this window that the observed PO by PN ratio in the shaded area 1 to 5, and black curve is our modeled PO by PN ratio, and our modeled ratio matches with the observation in the late warm-up and late post-warm-up phase. So in the hot core model also, we found that PO by PN greater than 1. So this is the summary of PO by PN ratio, which can be which could be said that it can act as a tracer of different evolutionary stage. And in our work, we modeled PDR region, diffuse cloud region, and hot core region, and found that our PO by PN ratio matches with the early modeling results by Jimenez-Serra et al. 2018, and also the observation results by Chantos et al. 2020. Sorry, they are also modeled, and Rivilla et al. 2020 and Rivilla et al. 2016. And then we calculate the IR spectrum of phosphine, and there was and previous work, experimental work by Turner and others in 2015, and we compare our results with their experiment, and we found an good match between the wave numbers and intensity of infrared spectrum of pH3. And we then check the other I species like CH4, CO2, CO, NH3, how they affect the infrared spectra of pure phosphine. And also H2S and SO2 are important in the Venusian atmosphere. And then these are highlighted part is the pure pH3 IR in the bending scissoring mode, and this is the stretching mode. And if you see that CO2 and SO2, they are affecting CO2 affecting the stretching mode of pH3 intensity, and also SO2 affecting the bending scissoring mode of pH3. So this could be helpful for future JWST mission. And then we move to the basic processes on interstellar grain surface, which includes, as I previously mentioned, that accretion, reaction, and desorption and diffusion. These desorption and diffusion, sorry, these desorption and diffusion directly or indirectly related to the binding energy of the surface species. And this binding energy dictate the position of the snow lines, which are formed during protoplanetary disk phase. You can see here the water snow line formed first, and then CO2 snow line, then CO snow line. And these positions are determined by the binding energy, and also binding energy are important to check the fate of interstellar species in the gas phase uh, in the ISM. So for calculating binding energy, first we consider benzene as a carbonaceous type grain. You can see our quantum chemical structure of benzene. There is H and H2, and silica on olivine type grain. This is the SiO2 cluster containing 3 SiO2 molecules, and water cluster as an interstellar grain mantle, where 6 water molecules considered as an water cluster to check H and H2 binding energy. And then we also calculate binding energy of several species. Here 16 stable species is shown. In this curve you can see that here we consider water cluster, different water cluster as interstellar grain mantle to check the binding energy of these species. And from this plot you can see that x-axis is the 1 2 3 4 5 6 increasing number of water cluster, and y-axis is the deviation from experimental value binding energy, and red line shows the zero deviation. And uh, you can see that the deviation is gradually decreasing when we consider uh, more large water cluster, that is water pentamer or hexamer. These curves also denotes the same. This is the average absolute deviation. It is decreasing when we increase the cluster size. Now, the topic of encounter desorption comes. Binding energy of surface species with water is usually provided in the and widely used in astrochemical modeling. So H2 would also cover some part of the grain mantle in the more denser and more colder part of the ISM. So previous literature values, H2 on H2 binding energy was 23 Kelvin, and H on H2 binding energy was 45 Kelvin. And our calculated values, where we calculated 95 total species on H2 surface, we find an opposite trend, where H2 on H2 67 Kelvin and H on H2 23 Kelvin. So considering this 95 total species, we compare that almost 10 times lower binding energy considering H2 surface than water surface. So then we plot considering encounter desorption and check that with increasing density, the effect of encounter desorption also increasing. And also with increasing temperature, encounter desorption effect is gradually increasing, and at 0.10 Kelvin temperature, encounter desorption effects mostly, and with increasing further temperature at 20K, it diminishes. So considering these 10 Kelvin temperature and 10 to the power 7 number density, we modeled and taking into account the encounter desorption of H2, and then the consideration of this updated binding energy shows a significant deviation in the abundance of the grain surface species, that is H2O and methanol. So encounter desorption should be considered to realistic model the environment. It is now moved to the next topic, where we study some interstellar ices. Interstellar ice constant contains H2O mostly of the order of 70%, then CO2CO of the order of 20 to 30%, and other 5% is CH3OH, NH3, and CH4. These interstellar ice can be categorized in polar ices and apolar ices. Different absorption band features of water ice significantly change with the impurity. Different types of impurities such as these, and we use various qualitative mixture different in different concentration ratio theoretically to carry out qualitative analysis of change of peak frequencies, intensities, and band profiles and band strengths of pure H2O. For this purpose, we know that the pure H2O band profile included libration, bending, bulk stretching, and free OH. The integration bounds are here noted in centimeter inverse wave number. And the ice mixture composition details, if you see the picture, we consider this type of structure for mixing in different ratio, concentration ratio, 20% to 50%, and then check the fate of these species, how they are affecting the infrared spectra of pure water. And some experiments were performed in Open University, UK, mainly for HCOH, NH3, and CH3OH. And we compared the experimental IR, which is denoted by red curve, with our theory denoted by blue curve. You can see a good match between these. Now I move to the biomolecule synthesis in space in dense cloud region. And these biomolecules could be a precursor of amino acids, and they can be bombarded via comets, meteorites to the early Earth. So first topic is the aldehydes and amines. We consider several isomeric group content, each group containing aldehydes and amines, each group containing several molecules, total 34 molecules we considered and calculated. I will explain in the next slide. Here you can see that methanamine and methylamine and ethanimine, they are amine and aldehyde already observed in the ISM, and they could be possible precursor of glycine suggested by early studies. Glycine is the simplest amino acid, and ethylamine, it is not observed till now in the ISM. It could also be an precursor to form glycine. So to understand the chemistry of amino acid precursor and complex organic molecule related species, these aldehydes and amines should be studied. For this purpose, since propanamine and ethylamine could not be observed in the ISM till now, we check their detectability, and for this we modeled again gas grain chemistry in the isothermal phase and check that propanamine and ethylamine, that is green curve and yellow curve, is not producing so much in the gas phase in the isothermal phase. And next we move to, for this we check their production in the warm-up phase, where temperature is gradually increasing from 10K to 200K, and these species sublimate from ice phase to gas phase according to their binding energy. And we check that propanamine and ethylamine, green curve and yellow curve, is producing much higher, of the order of 10 to the power -8. So from our modeling results and also from rotational intensity calculation, we propose these two molecules for future observation. So in this study, we find an important link between cometary and interstellar origin of ice. Altoy et al. 2016, they find methylamine, ethylamine, and glycine in the comet 67P CG from their observation. And they find the ratio between methylamine and ethylamine is roughly of the order of 1 to 15. And from our chemical modeling in the isothermal phase at 10K, we find that methylamine and ethylamine ratio of the order of 10 to the power of the order of 18. And this suggests this is something nearby, and this suggests that a chemical linkage could be possible between interstellar ice and cometary ice. So for this, more in-depth study is required to confirm this linkage between interstellar and cometary origin of these molecules. Then now peptide bond. What is peptide bond? Peptide bond forms when two amino acids react and then form this peptide bond. And this is the bond HNCO, and we consider three peptide bond related species: HNCO, NH2CHO, and CH3NCO. Isocyanic acid, and these are called the peptide like bond species, and they are also nitrogen bearing species, which would be helpful for biomolecules. And from our modeling study, HNCO, CH3NCO, and NH2CHO, we propose that these three peptide bond-related molecules are chemically linked. That is, previously suggested HNCO and NH2CHO are linked with hydrogen addition and abstraction reaction. That is, HNCO by hydrogen addition form NH2CHO, and again NH2CHO by hydrogen abstraction reaction forming HNCO. And these are the activation barrier of these reactions. And we also find from our modeling that HNCO react with CH3 to form CH3NCO. So these three molecules could be linked. So now I give my summary of our approach. And first we consider physical condition for which we want to model for like dense cloud environment or diffuse cloud environment. It is radiation dominated or radiation shielded. And then we implement this physical condition in our chemical modeling. And chemical modeling, for the chemical modeling purpose, we used gas grain chemical modeling for molecular cloud plot, and also spectral synthesis for cloudy for the diffuse environment or PDR or H2 region. And for the modeling purpose, these kinetics, binding energy, thermochemistry, reaction rates are calculated quantum chemically, or if available, we take it from experiment. And then from chemical modeling, we check the abundance of this species. And after that, we do radiative transfer modeling. And in between this, astronomical spectroscopy help to find rotational, vibrational, and electronic transitions of this species. And then we propose, depending on these parameters, that it could be a potential candidate for detection for future astronomical observation. And from radiative transfer modeling, we extract physical condition. And also here in our lab, we do observation data analysis, raw observation data analysis, from which we extract physical condition. So this is a cyclic process which we perform in our lab regularly. So I want to acknowledge my supervisor, Dr. Ankon Das, and I also thankful Indian Center for Space Physics for giving me opportunity to carry out my PhD research. And these are my collaborators. And also there is some. And I would like to mention Department of Science Technology, Government of India, for providing financial assistance through DST Inspire Fellowship to carry out my research. Thank you for your kind attention.
Okay, thank you, Milan. Now it's time for the questions. Please unmute your mic and you can ask questions.
Hey Milan, this is Raghav here.
Yes.
It was a nice talk. I just have a few clarifications. It's not a question. So for phosphine, you showed a time graph.
Yes. The evolution of phosphine in dense cloud environment, diffuse environment, and PDR region. Time graph is mainly for dense cloud environment. For we do hardcore modeling. Yes.
Yeah, in this, the dotted line, what is that one?
The dashed line is the modeling result of considering our calculated binding energy. The binding energy already available some in KIDA database. And since we are calculating our own binding energy quantum chemically, and we implement it in our model to check the fate of this species in the evolution. And we compare with the available binding energy. We also implement them in our modeling and check their evolution. And these dashed line are basically considering our binding energy.
So both are calculated values only, no?
Yes.
No, because while giving the talk, you mentioned it as observed. So I was like, how is it observed?
Observed is the PO and PN. these species are observed in the dark cloud region. So the observed abundance we noted from
Okay.
the, and this
Okay.
shaded region, blue shaded
Mhm.
region, is the PO by PN observed ratio, which is 1
Okay.
to 5. If you see the logarithmic scale, it is 1 to 5.
Mhm. Mhm.
And our PO by PN ratio, it is almost roughly 1
Yeah, it
to,
is in that region.
yes, in this region, it is matching. That is
Okay.
warm up and late warm up phase.
And then for the binding energy, you showed the percentage deviation from the experiments.
Yes. Yes.
Yeah, so it is like 0 is the ideal. So minus or plus, either ways, it is going to be a deviation from the experimental value, right?
Yes.
Uh, so as you increase it, it is not to say that more you take, the deviation is going to be less. So how do you decide how much to take?
Yes. For this calculation, here you can see the dimer configuration. 2 is for dimer. In our paper, if you see, we do not consider this dimer because
Okay.
dimer is showing an abrupt variation. And
Yeah.
this is the average absolute deviation in percentage, where and we also calculate the RMS deviation, where plus
Okay.
minus, yes.
Mhm.
And from that, we conclude that with increasing cluster size, the deviation is decreasing gradually.
Okay. So ignore dimer. That is what you're saying. Why is that deviation coming? Did you find the reason? I mean,
Actually, dimer, they some species like methanol, NH3, AHCl, some dimer, their binding energy with dimer is abruptly increasing with
yeah.
both monomer and tetramer.
Yeah.
And
Did you
some,
find any reason behind that? I mean, why it is
no,
abruptly
it
increasing?
is coming from our quantum chemical calculation.
Ah, okay. Do you think a scatter diagram will try to help, because negative or positive, you will see how much deviation is there? Okay, that we'll discuss later. And then there is this slide where you showed the ratio of water mixing and your
Yes, water mixing ratio. Uh, yes.
yeah. In this, for example, say now you have taken 4 molecules of water and 2 molecules of your pollutant.
Yes.
So 2:1 also, is it the same, like 2 molecules of water and 1 pollutant? Do you get a similar result, or
No,
uh,
actually, we did for only water tetramer, and
okay.
increase. If you see the water tetramer structure, there is 4 water molecule H2O, and there are available dangling hydrogen position to
Mhm.
connect with impurity 4, 1, 2,
Okay.
3, 4. So increasing this position,
Mhm.
we increase the impurity concentration.
Okay.
If we take 2 water molecule, that
Mhm.
is the dimer configuration,
Yeah.
then available dangling hydrogen position was 2, and we cannot add more than 2 pollutant in
No,
that
just
case.
one. I mean, just to say, like, is it only
Yes,
the
yes.
ratio that matters, or the number of molecules that matters? You see, because the difference between experiments and theoretical will be, in theory we use only very few number of molecules, and the experiment is actually in a bulk. So does only ratio matter, or the number of molecules matter, or how
Actually,
much deviation do we get?
actually, we want to check the band strength of this
Mhm.
pollutant.
Yeah.
So to calculate the band strength, we use this structure, and we check the trend of band strength, how it is coming from
Mhm.
our calculation. So
Mhm.
we do not investigate into depth using
Okay.
the huge
Yeah. Because since the
I think on band strength, the trend will be same using.
Yeah, band strength, yes, but you're also looking for the deviation, right?
No,
Due
in
to
this
the
case, no, in this
intensity. In the previous slide, you said that you're also looking for the change in the peak frequencies due to
yes,
impurities.
we calculate the IR spectrum, and from the
Huh.
IR spectrum, we find out the area under the curve to calculate the band
Mhm.
strength.
Yeah, so that is going to give you change in the intensity, right?
Yes, if you
But do you change
position,
any see any changes in the frequencies
yeah,
due
in
to the
some case,
impurities?
we implement dispersion effect to check
Mhm.
the uh, peak frequency changes. And but to calculate the band strength, the area under the curve is always similar. So trend of band strength is our main target to check.
Okay, okay,
So
okay. Thank you, Milan.
Okay, Raghav. Any more questions? Any more? If not, I have just a minor clarification. Milan, hello.
yes,
So in PO and PN and PH3 calculation, what temperature did you consider in the modeling? Temperature.
for diffuse cloud or PDR or hardcore model.
In three, you can just
Okay, for diffuse cloud model, you see that the red curve,
yes.
it is
Yeah, yeah.
the temperature. It is the temperature curve,
Yes, yes, yes.
and with increasing AV or depth of the
Yeah.
cloud, the temperature is also decreasing.
Okay, okay. Great.
So you see the variation of the temperature from
Yeah.
1600 almost to 10 Kelvin.
Yes. Yes, yes,
And
yes.
for PDR region, we consider in our modeling constant temperature. That is gas temperature 50 Kelvin and dust temperature 20 Kelvin. So red curve is showing a constant value in 50 Kelvin.
Okay.
Okay, and for the dense cloud environment region, we consider three-phase model, while isothermal collapsing phase, warm-up phase, and post-warm-up phase. In
Okay.
isothermal collapsing phase, the temperature is kept constant in 10 Kelvin. In warm-up phase, it is increased from 10 Kelvin to 200 Kelvin to produce a hot core. And in post-warm-up phase, it remains kept constant at 200 Kelvin.
Okay. Okay. So suppose you are increasing the temperature, the abundance will go or in post warm-up phase. Suppose you are going to 300
Yes,
Kelvin, what will happen?
yes, it sublimate from sorry, is the species can go with increasing temperature from ice phase to gas phase.
Yes, 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 yes. So you'll see more abundance in gas phase, I think. Right?
Yes, according to their binding energy.
Okay, okay, fine, fine. Still, we have time. If there are questions, they can ask. Fine, I think there are no more questions. So we'll thank Milan Sil. It was very nice talk. Thank you, Milan.